You can do it, but I wouldn't recommend it. So the last thing is something we can already cross out. If S is related to if S is not equal to null. So many people use this instead of that. It's the opposite of the if not P we've seen earlier, and it's also its evil sibling. So this one is evil, this one is evil as well, because what if does is it checks against a number. If checks if this is 0. So what if does is, oops, this is what if actually understands. When you write if S, it automatically does this. And comparing a pointer, since S is a pointer against a number, is equally as bad as comparing a character against a number. So this one is something I definitely wouldn't recommend. Also, this is probably not what you want to do, because this is checking if S is pointing, like it's not checking the character in here, it's not checking this, it's checking the value in here. It's not checking the value in here, it's checking in here, because you didn't put the star in front of it. The star is the thing that actually goes all the way to the value that you're pointing towards and returns the value back to you. So this is probably not what you intend to do. This is like either this or that, depending on the context, is the only way this would make sense. Otherwise, this is also bad, because this would be if star S is not equal to 0, which is exactly the same as this, and therefore also bad. So this one is the only thing, it also works for while statements, by the way. This one is the only thing that really makes sense in this case. And therefore, if you write something like this or like that, you might be referring to something else that also makes sense, like checking if this pointer is actually pointing to null, but you would write that differently. So for string iteration, though, you really need the star in front of it. If you left it away, well, S would never really be 0, because you keep incrementing it. Like a number would never be 0 just by adding onto it. Of course, the integer might overflow and you might get back, which is a bug or a technical feature in the system. But technically, this will lead to errors. So stick to this pattern, and then you're safe. But do you see the similarities between these two? They have a while statement. The condition is a bit different. The variable is a bit different. But in the end, you increment something, which is the counting variable that you're checking against, the left side. And in here, you have free space to insert another pattern. For example, you could take this pattern and put it in here. Doesn't make too much sense, but you can take this, put it in here, you can take this, put it in there. You're free to do such things. Don't look at code as a bunch of lines, look at code as a bunch of patterns that you can move into each other. And of course, when I take this and move it in here, you'll notice that this initialization happens inside of this loop. Every time this loop restarts, I get set back to 0. If I were to put I equals 0 to the beginning and remove it from here and plug this into here, I would never be set to 0 and keep incrementing on every loop. It would never be set to 0 because the only initialization is in the beginning. And if you don't pay attention to that as well, like having I equals 0 in the exact right place for your pattern, then of course you might have a number that just increments, and you might end up with values that you didn't intend to have because the number keeps getting too big for something or whatnot. So pay attention when you really write these patterns in the way they are written here, because otherwise if you say, okay, I equals 0 in the wrong place, these patterns might still be in the correct spot, but they're incomplete, and therefore they might give you completely wrong outputs. Do you see the issue here, or should I get into detail on that a bit more? Like, for example, when you plug this in here, you have the I equals 0 in here. So I increment S, and then I set I back to 0. And then I start this with I being 0 again. I start this loop, which is inside of here, with I starting off from 0 again. If I never did this, and I said I equals n, and this broke out and restarted, it would never enter this loop again because I is now greater than n, because that's why the loop terminated. But we get back, we don't set it back. I is still greater than n, so it won't even enter the loop, and it will just keep incrementing without doing anything. If you initialize I again, it will now be set to something, like will be set back to 0, will be less than n again, and then the loop will run. So this is a pretty nasty bug, because sometimes you just forget to do the initialization in the correct spot. Whoops. Yeah, this happens when the lecture gets too long. So, yeah. Pay attention where you initialize the stuff. All right. Iteration patterns. They mostly look like this. There are some minor variations on them, but this is the basic principle. You can put everything that you want to repeat inside of here, and whenever the exercise tells you that you have a sequence of data, might it be a string, might it be this, it's always this class of iteration patterns. When it tells you initialize this array with zeros, with ones, with some other value, do an iteration pattern. If it tells you calculate the length of a string, do an iteration pattern. If it tells you print every character in a string, again, every character in a string, 1, 2, 3, every character, it's an iteration pattern. And write the pattern first, and then decide what to do in there second. And in these, like with this mindset, the chance of having bugs is going to be reduced astronomically, because you'll never see statements that are bigger than this. You'll never see the and or and other conditions going on inside of there, and therefore the mental load when you write code is a lot less. And this is basically going to save your day if you are working on a really big problem. Okay, now I'm going to wrap up patterns now. I thought about making a list of these things online, so it's incomplete, but if you want to contribute to that, just talk to me. I'm going to give you the link later on. So there's more to that. Okay, last thing is pointers, which is what I'm going to touch just on the surface, but this might still help you. And once we have that, we will take a break for the week. Okay, questions about patterns? So yeah, the hardest part about the C language is technically the pointers, because people are not used to pointers. People are used to numbers, people are used to maybe lists of numbers, but pointers are something that is quite a complicated thing to grasp. And therefore, there might be an idea that's maybe a bit more, that you might be a bit more used to. So let's say you have a hotel, which has different rooms. Room number 1, room number 2, room number 3, and maybe a reception desk where a very nice person sits, and you can book a room. You can go there, tell that person, hey, I'd like to book a room for a night, or maybe 2, and you get a key with the room number, and whenever you want to use the key, whenever you want to access the location, you look at the key, it tells you, okay, it's room number 3, so you go there, open it up, put whatever you want inside of it, and close the door. And maybe if you have 2 keys, which is not that common, but some people do, then you can take the other key, open another door, put something in here, or take something out, and leave again, and maybe put it into some other place. So if you have the key, you have the location. If you don't have the key, you don't have the location. What I just described is a memory model, which is the model or the idea of how the computer organizes memory. So when you have, for example, 8 gigabytes of memory in your computer, you might have a hotel with 8 billion rooms, which is a lot to maintain. And each room has an address, has a number. Until 8 billion. So this is really how your computer works. You start out with 0, go to 8 billion, and whenever you have a program that's running, the only place where it can store its data is in here. let's say you have something like this. You have a function that does something, and you put an int x in here. This x will have to be stored somewhere in this memory. So what the system will do is, it will, when I write this, the system will automatically give us a room where we put our integer. So x goes in here, it still has its number, and whenever we say x, the system will run, open that door, fetch what's in there, and give us the value. When we say x equals x plus 1, it will go to x, get its value out, which might be 41. Does 41 plus 1, which is 42. And then, as you can see, it takes the 42 and stores it back inside of room number 5. There we go, door closed, calculation complete. Now, if we have a variable called y, it will be right next door. They're neighbors now. And y also has some kind of space in there where you can put numbers in. And if you have something else, like maybe a pointer, it will also be stored in here. Now, you might already see that you can put numbers in here, and numbers are also the only thing that you can put inside of these rooms. So when you have a pointer, what you have is a place where you can put a number. So pointers are like integers, numbers, and this is why it's so important to keep straight what numbers are and what pointers are. For example, in this case, that's the pointer, that's the number, so please use the pointer when you compare a pointer with some value. Again, the computer doesn't care. The computer could say, okay, null actually is represented as the number 0 in here, so if I say p equals null, I'm just going to put the number 0 in here because null somehow corresponds to 0. However, the C language has a reason why it has these things. And the reason for that is so that we as programmers don't have to care about the numbers that are behind this. The computer only sees the numbers, but